almost the rest of the semester. Okay, so we started talking about interference and diffraction, and here is a diagram that clearly shows the interference picture created by two. Okay, this will work. Let me just share it. Okay, so here it is. So you see that you have two sound speakers, A and B, separated by a certain distance. And if the observer is located at point C, this observer is going to hear what? Constructive or destructive interference when you're looking at the picture. What would be your guess? Constructive, clearly constructive, because you have two high pressure waves on top of each other. So you're going to have higher pressure. At the next moment of time, of course, both of those higher pressures are going to drop as the time goes by. And you're going, eventually this higher pressure is going to change with lower pressure from both speakers. In other words, you're going to have very large amplitude of variation of pressure, and this is what we interpret as constructive interference. We said that the equation that describes constructive interference looks like this. The path difference between those two waves, so the difference between this distance and this distance, call those distances L1 and L2, that difference of distances has to be equal to integer number of wavelengths. So n is equal to either 0 or 1 or 2 or larger number. Okay, so if we look here is the diagram that represents, well, in this diagram, instead of constructive, you see a destructive interference at point C. And the condition for destructive interference is similar. So you want the path difference between those two distances to be equal to semi-integer number of wavelengths. So you can write it either as, well, let's write it the way it is in the textbook. Odd number of half integer, which you're going to see that in a similar manner, it can be written as n plus 1/2 of lambda, where again n changes the way it is. Now, let me ask you the following question. In order to observe either constructive or destructive interference, the two sources of waves, in this case, the two speakers, have to emit exactly the same wavelength, exactly the same frequency. And the phase difference between those speakers has to be constant. Those are the ideal conditions for interference. What would happen if the two sources emit wavelengths with slightly different frequency. Are you going to observe interference or not? Best guess. Yeah, you're going to observe something, and actually I'll try to demonstrate it here with two sound sources. So you have two tuning forks, and this one is 256 hertz. See, 256 hertz. And you have a second tuning fork that originally was exactly the same frequency, 256 hertz, but that frequency is slightly shifted by adding those additions here to the tuning fork. So instead of 256, you probably have something like, well, maybe 260, let's say. And now, see what is going to happen if the two tuning forks sound simultaneously. You hear this, so you see that even though you don't have interference, still the two sources of sound interact, affect each other, and you detect sound intensity that varies with time. Let's try to, let's look at the diagram representing beats. Let's see, what is it? Maybe this one? Yeah. So you have one of the sound sources emitting the red, the other one the blue, and well, they have slightly different frequencies, slightly different wavelengths. The result is it is loud, dies out, loud, dies out. So this phenomenon is called beats. And we can, if we wanted, we can describe exactly the amplitude and the frequency of the beats, yes?
So does this also relate to harmonics? Because the reason I ask is because I play violin, and one way that we tune is we'll play a note, and if we have this oscillation of like loud and soft, then you can tell it's out of tune, but it's not being played with another string, if that makes sense.
Well, you're using this phenomenon in order to tune your instrument. So it is sensitive. It is very sensitive to a difference of frequencies. And of course, it is related with resonant phenomena. If there is no, we're going to talk a little bit about string instruments again in a few minutes. But that's a good point. So beats, this phenomenon is used in practice, in music, also in engineering. So if you have, let's say, not two sources of sound are very difficult if they are complex systems. They're very difficult to make them exactly with this perfectly identical. There are always going to be small differences between them. So, for example, two-engine aircraft. So they have two identical engines, but no matter what you do, you're going to have slightly different frequency in those two engines. Well, even slightly different frequency is going to generate this beat phenomenon. So it is you're going to have high vibrations, after that followed by no vibration, high vibrations, and vibrations with high amplitude are not healthy for the aircraft, right? They can destroy the aircraft. So in two-engine or multi-engine aircraft, in the past, the pilot was supposed to adjust the frequency of the two engines in such a way that they match perfectly and this beat phenomenon is avoided. Well, now most of this is done electronically, but as a phenomenon, this is something that you need to keep in mind. Okay, any other? Yes.
So the frequency and the wavelength are different, right? Both.
Yes. So wavelength and frequency are almost synonyms in this context, right? Because they're just connected with a single here it is wavelength, speed of propagation of the wave divided by frequency, right? Speed of propagation divided by frequency. So when I say exactly the same wavelength, it usually means also exactly the same frequency because the speed of propagation of the wave, the sound wave in air is a fixed number, pretty much. Okay, any other remarks?
Before we get too far ahead, there are two questions from the homework now that showed up in Zoom. So it's question 10 and 12 on homework 17.
Oh, this 10 is your question, right?
Yeah.
Okay, and the other one is 12. Let's see what is, yeah, probably now is the time. Yeah, let's look view homework 17 view. Let's see what is problem 12. Oh no, they don't ask about your problem, Albie. But they ask about some seeds. Okay, good. Okay, so probably now would be probably a reasonable time. Yeah, could you please share this to solve problem number 10 from the homework assignments because it is related with the formulas that are already on the board. So you have a row of seats parallel to a stage at a certain distance from the stage. And at the center in front of the stage is a diffraction horn loudspeaker. So what is diffraction horn? We mentioned it last time, but I probably have to repeat it again. The speaker sends sound through an opening that is, okay, so it is small doorway with this width. Okay. A tune that is exactly with this frequency, the speed of sound is this. Okay, so, well, problem number 10 is related with slightly with a different phenomenon that we call diffraction. Diffraction from an object. We talked about it last time, but let me remind you what we're talking about for the case of diffraction from an opening. Let's say that you have a wall, another wall here, and an opening in this wall with certain, with a rectangular shape, and let's say that this width of the opening is d. And now imagine that you have a sound wave, or any other wave for that matter, that is coming perpendicularly to the wall. What do you expect to see on the wall? Of course, the wall is going to generate to protect, to stop the sound. However, sound waves are going to go through the opening. And you would expect naively that, well, right, you're going to have certain intensity of sound waves here immediately in front of the opening, and no sound waves on the sides. In reality, the experiment shows that when the sound wave goes to the opening, the direction of propagation of the sound wave changes. So in addition to waves that are going to go horizontally, in addition to that horizontal direction, you see certain sound waves that are going, turning this way. Not only that, but if you're an observer on this side, let's say, at different positions along this line, and you move along this line and detect the intensity of the sound, or whatever wave you're working with, you're going to see that right at the central line, the intensity of the sound is going to be highest. And after that, it gradually is going to die out when you go away from the center line. So this is kind of okay, reasonable. What is unexpected is that after that, the sound intensity is going to grow again and drop again to zero. Grow again, drop again, and similarly on this side. So this pattern of intensity distribution is what we call diffraction pattern, and it has importance, well, not so much with sound waves, even though it is used, as you see in this diffraction speaker, but it is very important for electromagnetic waves for light. Okay, now, to describe the diffraction pattern from a wave with wavelength lambda, we are introducing this angle. So take the central line to the opening, and from the central line and the point here right on the opening, draw a line that goes to the first minimum of the diffraction pattern. This angle, theta, gives you a reasonable description of the intensity distribution on the other side of the opening. And it can be shown that sine of that angle, theta, is equal to the wavelength of your sound divided by the width of the rectangular opening. So this formula is not so difficult to derive and make an argument that this is what it should be. But for the moment, we're going to get back to it when we talk about electromagnetic waves. Well, a similar phenomenon is observed if instead of rectangular shape of the opening, you have a circular shape with a diameter d. In that case, the formula has to be slightly modified. So the formula looks like this for circular opening. Sine of the angle theta is equal to 1.22 times lambda divided by d. And now, once we have those two, so look, this is a strange phenomenon. This diffraction of sound. It basically predicts that when I'm talking here in this direction, let's say with certain fixed frequency, maybe using a tuning fork or something, and here is the rectangular opening over there. And if you're right across the opening, you're going to hear the sound clearly. However, if you go a little bit off the center of the opening, you're going to find a spot where the sound is going to completely disappear. Well, this may contradict to your experience, but the contradiction is due to the fact that most of the sound sources do not emit a single wavelength, single frequency. most of the sources emit a range of frequencies. So the diffraction pattern for those different wavelengths is slightly different. So if you are located here and you don't hear one particular frequency, you hear the neighboring frequencies. And your brain can reconstruct the rest of the sound. Okay, so now let's questions and remarks about diffraction. Okay, so again, we're going to go back to diffraction from openings when we talk about diffraction of light. So problem number, which problem is that?
This is 12 right here.
No, but 12, let's do problem 10.
10.
Let's,
10 was the one that.
yeah, let's first do problem 10. Is this problem 10 or which problem is that?
This is 10. Right
Okay,
here.
so you have seats parallel to the stage at a certain distance. At the center of the stage, you have a loudspeaker, diffraction loudspeaker. And that loudspeaker has opening that looks like a doorway with given width. It is playing a single frequency, which is given. Speed of sound is known. What is the distance between the two seats where the sound cannot be heard? Let's see. So this is problem 10. Here is the stage, here is the row of seats, and here at the stage you have a speaker with rectangular opening. I guess here it is, rectangular opening speaker, diffraction speaker. So they say that the width of this opening, rectangular opening, is given. The width is D from here to here. So this is opening. And you are given certain distances. So the distance from here to here, for my version of the problem, it is 8.3 meters distance. So call that distance some, let's say, call it X, okay, X would work. Well, our alphabet has a limited number of letters, and most of those letters are reserved for different variables, so it is always. So when we run out of letters from the Latin alphabet, I can start using Greek. When we run out of Greek letters, it is time to start using Bulgarian letters. And I have a favorite Bulgarian letter. The letter O looks like this. O. Okay, so that's very nice sound, easy to pronounce. But for the moment, let's stick to X. Okay, X for me is 8.3 meters. Okay, and diffraction loudspeaker, the doorway, the width is capital G equal to 0.074. 0.074 for my version. And the frequency of this sound is also given. The frequency of the sound for my version is 40 kilohertz, let's say. This way. The speed of sound is given. 343 meters per second. Therefore, the wavelength of this sound wave is V divided by F. which you can calculate to be 343 divided by 40 times 10 to the third. You can get a number for that wavelength. And now look, the speaker is on. You're going to have high intensity sound right here at the center, right here. But the sound intensity is going to be different as you go off the central line. Eventually, you're going to have no sound at this point and no sound at this point. And of course, you're going to have after that secondary maximum, but they're asking about this distance. So this is the distance that we are supposed to find. Call that distance y from here to here. And this is what we're supposed to determine. And of course, now, once you have the diagram, the problem becomes purely a geometry problem. You have this angle theta, you can determine, right? Sine of that angle is lambda divided by d. Lambda is calculated, d is calculated. You can find this angle if you want. But it is easier to apply to look at the diagram and find this distance, because you can say that sine of your angle is lambda divided by d. Therefore, the angle itself is inverse sine of lambda divided by d. And once you have that angle in radians or in degree, your choice, you can go back, look at this right triangle, and from the right triangle, you see that the ratio of this to this is exactly tangent of the angle theta. So you can say the ratio of y divided by 2 divided by the distance x, which is known as 8.34 my version, is exactly equal to tangent of the angle that you already found. And therefore, you say the distance y that we're looking for is equal to 2 times x multiplied by tangent of the angle theta. And this should be the answer. This should be the answer. Okay, let's see questions and remarks. Okay, so we have sufficient time to finish the last section. Here is standing wave section, and so it is one particular application of interference of waves on a string, transverse waves on a string, just like the violin and all other string instruments. So here is the string, and look, if you create a disturbance on this side, like this, let's say, and let it go, that disturbance, it is not quite clearly visible because it travels quite fast and it dies as it goes. But that disturbance is going to travel, get reflected from this end, and come back. So if I keep creating disturbances on this side, those disturbances travel this way, while the reflected disturbance, the reflected wave is traveling in opposite direction. As a result of that, you have now two waves that are propagating in the same place at the same time, and therefore they are going to interfere. So in most cases, that interference pattern is not going to look like anything interesting, except when the disturbance, the original disturbance has some particular frequency. So if the frequency of the original disturbance is appropriately chosen, you're going to see that the interference pattern of the two waves is going to have a stable shape. And the first shape that is easiest to observe is the first so-called first harmonic. It looks like this. So the first harmonic looks like this. Here is the string. Let's make it shorter. Here is the string with length L. The first stable interference pattern is going to look like this. So the string is going to oscillate if the disturbance has appropriate frequency. The string is going to oscillate with high amplitude in the middle, and of course the two ends of the string, which are fixed anyway, are not going to oscillate at all. So we call this a standing wave, first harmonic or fundamental, and you can determine the wavelength of this oscillation just by looking at the picture. So look, this looks like, well, part of a wave. If you want, you can continue it. And here it is. In order to get the entire wavelength, you need one more length. In other words, the wavelength of this first harmonic is equal to 2 times the length of the string. Just from the picture, this is what is visible. Well, of course, since it is the first harmonic, let's call this wavelength lambda 1. Let's see what is the corresponding frequency. So you remember that wavelength is speed of propagation divided by frequency. Therefore, frequency is the speed of propagation divided by wavelength. And therefore, the frequency of this standing pattern, the frequency of oscillations, is going to be F1 is going to be the speed of the wave in the string divided by 2 times the length of the string. So again, the speed of propagation of the wave on the string is not the speed of oscillations. It is the speed at which a disturbance created at this end is going to propagate to the other end of the string. For some of the questions in the homework assignment, you have to recall that the speed of propagation of a wave on a string, transverse wave on a string, the speed of propagation is given by square root of the tension force in the string, how hard you have tense that string, divided by the mass density of the string. So the mass density mu is the mass of string material divided by the length of the string. So this formula you're going to need, and of course, this formula has its relation to string instruments. So you can make the strings increase the tension force, decrease it. You can have strings with different thickness. All of this is going to result in different speed of propagation, and therefore it is going to result in different frequency emitted by that string. Fundamental frequency. Well, under, yes,
So F is tension force or the force that you applying to the string?
so it is the same thing. So F is the force, how many newtons I'm pulling right here. Right? If I pull with 10 newtons, F is 10. So I have to pull this string in order to, so the tension force F cannot be zero, right? If I let it like this, there is not much elasticity anymore. It's not going to work at all. So the harder you pull, the better the elastic properties of the string, and faster you're going to have the transmission of any disturbance from one end to another. Okay, any other remarks? Well, now the same string, but now I can try different frequency, different from the frequency that I initially discovered the stable standing pattern. And again, the experiment shows that if I double the frequency, I'm going to observe another standing pattern that looks like this. Here's the same string, but now the stable standing pattern, due to the interference of the wave that I create and the reflected wave, is going to look like this. In other words, you're going to have oscillations with high amplitude here and here, and no oscillation of the string at all right here in the middle, and of course at the two fixed ends. This is what we call second harmonic. And you see that this is exactly one wavelength, and you can say that the wavelength of the second harmonic is exactly equal to the length of the string. And therefore, you can say that the frequency of oscillations of the second harmonic is equal to B divided by L. The points at which the string doesn't oscillate, and this is one, this is the other, this is the last where it doesn't oscillate, those points are called nodes. And the points with the maximum amplitude of oscillation, those 2 points right here, are called antinodes. So the second harmonic has 3 nodes and 2 antinodes. The first harmonic, the fundamental, has 2 nodes and 1 antinode. And I can continue with this game. I'm going to try different frequencies on this thing until I hit some stable interference pattern. And of course, you can already guess that the next frequency at which you have a stable interference pattern, the pattern is going to look like this. So you're going to have here and here. The pattern is going to look like this. You're going to have, in other words, you're going to have 4 nodes and 3 antinodes. The wavelength of that pattern is going to be, what is it going to be? 2L divided by 3. The frequency corresponding to this third harmonic is going to be V divided by 2L and multiplied by 3, and so on. You can continue with higher and higher harmonics on oscillating strings. So this is lambda 3 F3. The general expression looks like this. The wavelength of the nth harmonic is equal to 2L divided by n. N is integer number 1, 2, 3, 4. And the corresponding frequency Fn is equal to n times V divided by 2L. So usually this is a formula that is. So in the case of string musical instruments, you are tuning to the fundamental, the first harmonic. However, how the instrument sounds depends upon a smaller, higher end harmonics. And depending upon the shape of the instruments, the size of the instrument, different higher harmonics are going to have different strength. And this is why a violin sounds different from viola or from guitar. This is the reason you have different sounds. Okay, we have 5 more minutes. I know that I was supposed to solve at least one more homework problem, but before, that homework problem is related with standing waves in a pipe with either 2 open ends or 1 open, 1 closed ends. And this standing wave on a pipe, okay, I cannot generate, but the reasoning is very simple and similar to what we had for the case of transverse wave on a string. So look, here you can generate a sound wave, and you can observe a stable interference pattern. Let's say you generate a sound wave on this end. This sound is going to propagate this way. And when it reaches this open end, it is going to get reflected from the open end. So you always have reflection when a wave encounters a medium with different properties. And the properties of air in the open are slightly different from the properties of the air inside. As a result, you always have a reflected sound wave even from the open end. Now, that sound wave is going to interfere with the sound wave that I generate here. They're going to interfere in the middle, and you're going to observe a stable interference pattern. For sound waves on a pipe with 2 open ends, the first stable interference pattern, the first stable pressure pattern, the first harmonic looks like this. So here is the pipe with length L. The first stable interference pattern looks like this. You're going to have high variation of pressure at the 2 open ends of the pipe. And the pressure is going to be constant, equal to atmospheric pressure in the middle of this pipe. So this is the first harmonic for a pipe with 2 open ends. And you can see that the length of this first harmonic is exactly equal to 2 times the length of the pipe. So you have to, if you take this picture and double it, you're going to get exactly 1 wavelength. In other words, the wavelength of sound in this pipe with two open ends is exactly equal to twice the length of the pipe. And the frequency, corresponding frequency, is also the same expression. Here, the speed of the wave v is the speed of sound in air. In a similar manner, you can make the argument that the second harmonic is going to look the following way. So you're going to have a stable pattern that looks like this. You have antinodes always at the open ends, and you have another antinode in the middle of the pipe. This is the second harmonic. And of course, nodes are here and here. Again, this is exactly one wavelength equal to the length of the pipe. And therefore, you have, for the second harmonic, the frequency is given with this formula. And so on. The frequency of the nth harmonic in a pipe with two open ends is going to be exactly given with this formula, the wavelength with this formula. Now, the things are slightly different when instead of a pipe with two open ends, you have one open and one closed end. And, well, I'm going to draw the picture of standing waves in a pipe with one open and one closed end on Monday. And on Monday, again, our main goal is going to be introduction to electrostatics. So we're starting electrostatics on Monday. Please look at the homework problems, and I'll try to solve at least one or two more homework problems on Monday from chapter 17. Have a nice weekend.
What was that? Oh, okay. Yeah. Dr. Tatar?
Yeah.
I think there's a question for you over here.
Yes, yes. I'm listening. Yeah. Begin also. One more question I have. Oh, the brownie points. So the brownie points, I have to have a final class list. And there are two people in the class that were not able to get WebAssign account. But on Monday, I'm going to put the brownie point list. I'm going to send an email to people next week. And all the brownie points that you have accumulated, you can add them when you get the email with the link to Google Docs. Okay?
Thank you.